be solving another physics theory problem or two problems. The first problem is going to be on rocket planet of mass m, and you have a small rocket of mass little m, and their closest distance is d, and the rocket is moving with a velocity v on a parabolic orbit. This is a parabolic orbit, and you have to calculate what is the distance of closest approach in terms of v, m, and capital M. So good luck.
Okay, so that's pretty difficult, I think. But first of all, I mean, we have to like figure out how this works. So we have M right over here. This is our distance of closest approach, and this is little m. So I'm kind of treating this like something on the xy plane.
Yeah.
So let's see. How do we actually quantify this? Oh, wait a second.
If you want to hint this, you can use two hints.
Okay. So
or you can ask the audience.
So let me think. Obviously, this is gonna be right here, and the velocity is v at that specific point.
That's true.
What is he trying to find?
He's trying to find the distance of closest approach
v
in terms of
velocity.
and
Velocity is perpendicular with respect to the centripetal acceleration.
Yeah, but the centripetal acceleration isn't constant.
Oh.
Okay, so let's see.
Genius makes a startling revelation. Yeah.
Sometimes you gotta know when to keep your mouth shut before a fist goes into it. Okay. I think maybe the best thing to do would be, well, the horizontal velocity is always, no, it's not always constant.
Even though you're trying to look for something that's constant. No matter what, there's always one thing that is constant. What is it?
Mass?
Well, I mean, yeah, but mass is not like a quantity.
Rest mass, you mean?
Please don't. Okay.
Oh, actually, Dad gave you a hint. Take the hint.
Rest mass?
Yeah.
Which is related to what?
Relativity?
No. Related to what? What is rest mass? Can you write down the rest mass formula?
It's just the mass. It's just the mass of the
What is the energy related to rest mass? That's what I'm trying to say.
I forgot.
It's just. Oh. So what is conserved always?
Energy.
Energy. So can you write down the energy, the total energy of the rocket?
Oh crap! Okay. So I mean, you've got the kinetic energy, you've got the gravitational potential.
Okay. There's one thing that most people forget about. Yeah, there are two parts, but there's actually one additional term, not just kinetic and potential.
What else?
Do you want a hint? This one might be non-trivial. Can you write down what you think the total energy of the rocket is?
I mean, what are the two sources? It's potential energies, the integral of force over distance.
No, you can just write it down. Just write down what you think the total energy is.
I mean, it's just half mv squared minus gmm over r, right?
Okay, so now can you draw a plot of this? Can you draw a plot of the potential energy? Potential energy against R, if you have it.
I mean,
okay. Now, what relates potential energy to force?
Just this, right?
No, it's not an integral.
Oh, potential energy to force.
Yeah,
it is.
It's not an integral. It's a derivative.
Oh well.
Yeah, but force is the gradient, the negative gradient of potential.
Well, yeah, it's the same thing, the same.
But this is the conventional way to write the relationship between force and potential. Now you look at this graph and tell me what happens to the force as r approaches 0.
I mean, it's going to approach 0 as well, since the slope is approaching 0.
No, as r approaches 0.
Oh, as r approaches 0, it approaches infinity.
Okay, now what does that mean? See, draw the slope.
Oh, here. As you get closer and closer,
yeah,
the force gets larger and larger exponentially. Well, not exponentially, but
Well, you look at the slope here. What is the slope when r is very close to 0? Let's look at a point here. What is the slope?
I mean, the slope is just GMM over R
No,
squared.
is it positive or negative?
It's negative.
No, this is a positive slope.
Oh, this is positive, but I mean
So,
taking the negative sign. It's
That means the
negative,
force
so-
is negative, right?
Yeah.
So that means, basically the rocket is gonna fall into the planet. Okay, the rocket will fall into the planet if there's only gravity. But that means that this obviously doesn't happen for the parabolic orbit. That means there
Well,
has
wouldn't
to
that
be
be assuming it has no horizontal velocity?
no. Even with enough horizontal velocity, this model tells you the rocket will fall into the planet,
Okay.
and clearly that's wrong.
So what else is there? Like centrifugal force?
Something like that. So the total energy is actually 1/2 mv squared minus gm m over r.
Yeah.
Plus L squared over 2 mr
What's
squared.
like
Where
the
does
black
this
hole,
come
the
from?
black hole short cell radius?
That is not the source.
You could get Rorschach radius from this one with a few tricks.
I mean, you
But-
can get any physical quantity
That's
from
true.
this, basically.
From with a few tricks. But look, this new term is the angular momentum potential energy.
But
And where does it come from? Where does it come from?
Wait, angular momentum. So that's wait, like kinetic rotational energy, or
That's right. That's basically what this is. But we call it a potential energy term
and
because
what's
it
L?
depends. L, you should know what L is.
Length.
No, L is angular momentum. It's a conserved quantity.
Why are you using lowercase l?
That's the convention.
What?
We use that's what we use in the physics textbook. Or if you
Literally, all my
if you-
life I've been told it's capital L.
okay, if you want to use capital L, then okay, what is L equal
I
to?
mean, I omega.
Or what else is it equal to?
Wait, okay. I mean, this is m.
In terms of mass.
Oh, in terms of mass, I
Yeah.
mean, wouldn't it be, and omega is v over r. So wouldn't it be mvr?
MVR. Can you plug that in here? See what you get?
I mean, you get m squared, v squared, r squared
Mhm.
over 2mr squared. So these cancel, and you get mv squared over 2.
What is that?
Oh, that's
Half mv squared.
Yeah. So you see, this is just a rotational version of half mv squared.
So that is k rho.
This is the rotational kinetic energy, but we put it with the potential energy term because it depends only on radius, not radius dot. So this
Wait, is that half L over I? L squared over I? I mean,
L squared. It would be I squared.
oh wait,
omega
no,
squared.
this is so this is
This
I
would be
omega
half I
squared.
omega squared.
Oh yeah, so
So just
that
another
would
way
be
to
just-
write the same thing.
Okay,
So
so
this-
there's
this
kinetic
here
rotation
is the effective potential energy. Okay, this is what we call the effective potential energy.
but isn't this
and-
kinetic?
We group it with the potential energy term because it doesn't depend on r dot. This
Oh,
depends on
because
r dot. Kinetic energy always depends on r dot.
okay, got it.
Potential energy only depends on r. So now, can you draw the new PE graph with this term?
Well, with this term added, this is plus.
Mhm.
Okay, so I mean,
It might be a little tricky, so if you need.
I think it would look something like this.
Yeah, very good. Very good. So can you explain how you came up with this?
I mean, at the beginning, r squared is a lot less than r when you're very small. So
Mm.
that means that this fraction is going to be a lot bigger than this fraction, at least ignoring the tops.
Mm.
But as, of course, r grows bigger, r squared eventually becomes greater than r, which means that at some point, the fraction with r squared on the bottom is going to become less than the
Mm.
fraction with r on the bottom.
How do you know this is bigger in the beginning?
Well, I mean, we know that r squared is less than r.
But this is 1 over r squared.
Yeah, so just dividing both,
Mm.
flipping both sides, you get this.
Mm.
So then the negative side takes
So
over.
r
the
squared.
negative side
So
gets
1 over r
smaller
squared is
too.
greater than 1 over r only when r is less than 1.
Yeah, exactly.
So you're saying
And that margin
Okay.
becomes smaller when you add all of those coefficients.
okay. So this is the correct potential energy plot. So look. So this is the radius and this is the effective potential energy. Now, so this type of orbit, what type of orbit is this? Let me draw it here because it's important. Let's draw it here. What type of orbit is this?
Okay, well, if
No,
potential
yeah,
energy increases,
What kind of orbit is this?
oh, this is flat, so the force is definitely equal to 0 at this specific point in time. Wait.
No, this is not against time. This is
Oh
against
crap! Okay,
radius.
sorry, I'm dumb.
I
mean,
I can
what's
give you
DVDR? That's like GMM over R.
here. I give you 4 choices. There are only 4 types of orbits.
What is that?
This is a circle, ellipse,
Okay, yeah,
parabolic, hyperbolic.
Oh, okay.
What type of orbit do you think this is? Parabolic.
Okay, that's the easy answer, but like,
But look,
you have to think
there's only one radius.
It's like because
There's
a
only
parabola only has one vertex, and then it keeps trailing off, right?
Yeah, but there's only one
There's
radius.
one maximum.
This is actually a circular orbit.
What?
This is a circular orbit because a circular orbit has the least energy. In physics, the circular orbit has the least energy. Now, what type of orbit is this?
Oh.
How many radii does it have?
Oh, 2. So that's an ellipse.
This is an elliptical orbit. Ellipse. Do you know what this is called? Distance of closest approach?
That's perihelion and aphelion.
Yeah,
right?
this is periapsis and this is apoapsis. Now, what is this orbit?
I mean,
You see, there's only one. The energy is 0.
Oh yeah. So it takes one. Oh, so like for a circle, it settles around here.
It's a
For
stable orbit. Yeah.
for an ellipse, it kind of jumps between these two.
Yeah.
But for the parabola, it goes past this once and then keeps going on forever.
There's only
It's kind of like a roller coaster.
So this is a parabola.
Yeah.
This is a parabolic orbit. And then what is this?
I mean,
This is a hyperbolic orbit.
how would you determine the difference?
Because energy is greater than 0, energy is equal to 0, energy is less than 0, energy is less than 0. Eccentricity equals for a circle?
0.
0. For ellipse?
I think somewhere between 0 and 1.
Between 0 and 1. For a parabola?
1.
And for a hyperbola? Greater than 1.
Okay.
So, in this problem, it tells you what kind of a orbit is it.
Okay.
What kind of an orbit is it? Parabolic orbit. So that means the total energy is
0.
0. So can you make the energy 0?
Okay, so if the energy is 0, we just have half mv squared is equal to gmm over r minus l squared over 2mr squared.
But there's one more thing you can do.
What?
When a ball is going from up to down, what is the velocity of the ball? Vertical velocity.
What do you mean?
When a ball is going from up to down, changing directions.
That's 0.
Yeah. So what is v?
I mean,
At closest approach.
It's not 0 because there's still a velocity tangent to it.
No, that's true. But r dot.
Oh yeah, the change in the radius is 0.
R dot is 0 at that instant in time.
Yeah, like locally, you can also see that it looks kind of like a circle.
Yeah. So what is the kinetic term there?
So wait, the kinetic term at closest approach?
Yeah, because that's what we're doing at closest approach. 0.
Wouldn't it be 0?
Now can you solve for?
Oh, okay. So now that's what really simplifies the problem. No, it's not doing so well. Okay, so let's see. I mean, you have, and what are we solving for again?
You can solve for either the distance of closest.
Distance of closest approach. Sorry. Okay, so of course you can just cancel that out on both sides, and multiply both sides by 2mr to get 2gmn squared r. So you just have.
Remember, L itself has an r inside.
Yeah, I know. Oh crap. Yeah, so You can't really do that. This is I omega, which is MVR at the end of the day,
But it's L squared.
right? Oh, so we never needed the mass in the first place.
Now you see.
And the radius reduces to 2g. Hey, that looks a little bit familiar.
Okay. Yeah. Square root it.
This is R.
Oh, that's R.
Hey, isn't this the Schwarzschild radius?
That's what I was.
That's what Dad was saying in the beginning.
Yeah, but like that, this is definitely not the Schwarzschild radius.
No, it's not, but it's a funny coincidence. Okay, now how can you get the same answer in 5 seconds without doing any of the math?
Wait. Because I mean, this has just enough velocity to escape from its orbit after closest approach. So wouldn't that? So
by the
wouldn't-
way, do you know
No.
Schwarzschild's son is studying at Princeton University? And
Martin
Carl-
Schwarzschild.
Huh?
Martin Schwarzschild.
Yeah.
he's still alive?
No, his son.
His son
No,
was.
his son is still alive.
Yeah, unbelievable.
You know how old Carl Schwarzschild is?
He died during the World War One.
Yeah, that
Yeah.
guy is like.
Unbelievable.
His son must be at least 80 by now.
How can his son be alive? Is his son or grandson?
Oh, it's,
Yeah,
if
maybe
it's his
grandson.
grandson, he's probably still alive.
Yeah.
Child, I just love him.
I guess, I mean, the easiest way to do it in 5 seconds would be to
Escape
realize,
velocity.
yeah, I mean, for a hyperbola, you just go and leave. But for a parabola, you slow down, have this one point of closest approach, and you have just enough velocity to escape, which means you just use the escape velocity formula.
But that will give you square root of gm over r, not square root of 2gm over r.
Really? What?
Yes. Uh-huh.
No, that's
Yeah.
a lie.
Yeah.
No, you're
Yeah.
lying. Dude.
No.
You're lying.
You can do the math. You don't have to believe me.
Oh, okay. GM.
1 second, I take that back. Yeah. Okay. No.
What do you take back?
No, I
mean, like, it wouldn't make sense for this to be in the Schwarzschild radius, which
No.
is literally just solving for radius in the escape velocity formula.
yeah, that's true. But do you realize?
Why you are not solving the problem? You don't know how to solve it?
We
Oh,
just
no,
solved
he
it.
got the answer.
Oh, the answer. Okay,
He
all
got
right.
the answer.
So, what do you wanted to find? Can you just give a summary?
We wanted to find, like, the distance of closest
Distance
approach
of closest approach.
in terms of the
So,
velocity
can,
at that point.
some people want the numeric value. So, can you be mass?
We don't have any numeric values given.
Let mass be 2.
This is so ad hoc. If someone wants to just plug in
You
values,
could-
let them do it themselves.
You could do numerical estimation like this. So v squared is
Well, I mean,
2gm over r. G is 6.67 times 10 to the minus 11
these
and
guys are gonna.
is 10 to the 24.
Newton
for the
meter
Earth.
square. Newton
And
meter square.
Damn!
kilogram is square.
These
And let's
rockets
say-
are getting real compact.
yeah,
One
and
is
then
only 2 kilograms. That's
let's
actually
say-
crazy, bro.
let's say r is
10 raised to 6. If it is
yeah,
not.
1 million meters away. Is that reasonable?
Yeah, Earth is 10 raised
No.
to 6.
We're not doing
No,
the Earth.
we're not doing the Earth. How far is the rocket away at closest approach? Let's say 10 to the 5 meters.
Yeah, but
Okay,
aren't we?
never mind
So-
with numeric
Yeah,
value.
but plugging in a numeric value means nothing.
And
You can
anybody
do it
can do
yourself.
that.
10
Okay,
to 13.
alright, so
Oh, yeah, I got it.
What are you doing?
But I got it.
you don't need to.
Genuinely,
No, I got
what are
it.
you doing?
I got it.
What are you
I
doing?
got the velocity at closest
What are you
approach.
doing?
Big
Let me-
baby,
let me
big
write.
baby,
It's just
Yeah,
like
he
10
is a
to-
big baby.
big baby.
It's
Just
just 10 to the 4.
I know you love number, but not everyone does.
10 to the 4.
Okay.
I love numbers more than you do, and even I don't want to.
I don't know what numbers